Hello everybody. We can do more advanced studies on the trace heating, especially the transient trace heating. What I mean is to look into details of the heating curve and to talk about pulse-width-modulation, PWM. Maybe you remember the model from the last video. It's a calculation of the heating curve of a very simple setup. Just a trace, 11 amps input, minus 11 amps output, 3 monitor points, 4.6 millimeters wide, and the expected temperature is 40 degrees, which means 20 degrees above ambient, which is precisely the value from IPC 2221. I've calculated a transient heating curve with a lot of time steps around 0 so that the rise of the temperature is very well reproduced. This is a short animation of the situation. And let me show you what we can get out of that data. Go to Extra, start the PWM post-processing option, and I'm selecting the report Excel file, which is created during the calculation. And I know that the previous power in the trace was 1.17 watts, and this is the import of the curve. We can treat the curve somehow. For example, derive a cooling curve and modulate the heating curve with on and off values of current or power. But first let me show what we can learn from the calculation. The heating curve is not spectacular, but what is spectacular is this plot. It's called the thermal impedance versus time, especially the log time and the log thermal impedance. Thermal impedance is just temperature minus initial temperature divided by the power. In the double log diagram, we see a curve which has some kinks. This means that we have at least 3 cooling regimes. Regimes in terms of numbers, which means we have a spectrum of RC values, not only just one. And the time constants are 0.32 seconds, 4 seconds, 20 seconds, and 100 seconds. If you have a closer look at the data, you can identify the values. 0.3 seconds is the time constant of the hotspot in the center of the trace. 4.2 is the time constant for the trace. 20 seconds is the time constant for moving the heat from the trace to the board. And 100 seconds is the time constant of the board itself in the ambient environment. Now let us talk about pulses. Of course, we could create a transient setting with on and off values as much as we want to have, but this is of course very CPU time consuming. Much more effective method is to do a mathematical approach. Say we define time intervals and convolute the heating curve with this power curve. For example, we want to say we have a time interval of 1 second on and a time interval of 0.3 seconds off. The power value in the on state is say 1.17, which means 11 amps. and the power in the off state, half the current. Half the current means 1/4 of power. So I'm dividing 1.17 divided by 4 is 0.29. Let's say 0.3. We give the number of periods. The number of periods should be 50, for example. This is the preview of this convoluted curve. And without consumption of many hours of CPU time, we get a nice result. On the average, the temperature should be as it comes from the RMS value of the current or the power. But from the RMS value, you cannot get the peaks and the lows. The IPC Trace, of course, is an academic example. This one is a more realistic board. It's part of the TRM manual. It's a 2-layer board with some components on top, almost nothing on bottom. I added some amps to some of those pads. We can see it from the table. It's 5 amps, minus 5 amps somewhere, 1 amp, minus 1 amp. And to watch it, this is plus 5 amps. X5 got minus 1 amp, and the trace goes like this. And this pin got also 1 amp, and it's terminated here. Let us calculate the heating coming from 1 amp here, 1 amp there, and 5 amp there. Of course, I prepared this result, and the temperature plot is like this. In this case, they heat up each other, which means that the single temperature of this trace would be of the order of 45 degrees, same as this one. But here we have some multiplication of temperature. The voltage drop can be seen from this graph. Voltage is 114 millivolt and minus 150 millivolt, so the total voltage drop is 264 millivolt, and similar values for this trace. We can of course create a heating curve for this, and I will do this in we simply say transient, start the calculation, define our time grid. The time constant is 100 seconds estimated. Let us choose 500 seconds for the final time, and the first step should be 1 second, the factor of progression 0.2 or 0.3, which is some standard value. We have to calculate 20 time steps and be patient. The calculation is done. We watch the results. For example, temperature, same values as before, but we have a transient curve with the maximum temperature as black line, a thermocouple on X9 trace and another thermocouple at X5 trace. Here we see what is called a trace fuse. There's a trace with a narrow part. The narrow part, of course, produces more heat, maybe an excess of heat, causing the trace to melt. This is the infrared experiment, and this is my simulation approach. For trace fuses, you have to take into account the coupling between temperature and material properties, because specific resistivity of copper rises with rising temperature. This is another story, but it's manageable.